Welcome back to Bio 6612. I'm going to talk today about comparing logistic regression models. So the material in this lecture is the last material you need in order to complete your second homework assignment. And today we're going to cover likelihood ratio tests for logistic regression and AIC and BIC. So generally, we might want to run a couple models and be able to compare between them to decide which is the better model. And for nested models, as you would in linear regression, a good way to do this is using the likelihood ratio test. And as a reminder, a nested model is, when you have nested models, you have a reduced model, which is a model with fewer covariates, and then a full model, which is a model with the same set of covariates as in the reduced model, plus a few more. And yeah, we can use a likelihood ratio test to compare nested models, where we take a ratio of the likelihood under the reduced model over the likelihood under the full model and take the log of that times -2. And this test statistic will follow approximately a chi-squared distribution where the degrees of freedom is equal to the number of parameters in the full model minus the number of parameters in the reduced model. And one thing I didn't talk about when I talked about inference for logistic regression is you can actually use a likelihood ratio test to test a single parameter. For example, beta 1 equals 0. In lecture 4.1, we talked about confidence intervals and hypothesis tests for betas using the Wald statistic, which is what the default test statistic is using R or SAS. But you can also use the likelihood ratio test to do that. And actually, the likelihood ratio test can have better power when the sample size is small. However, you can one thing that you can do for the likelihood ratio test that you can't do with the Wald test is you can use it to test several parameters at once. For example, beta 1 equals beta 2 and both equal to 0. And using the likelihood ratio test to test several parameters like this is equivalent to comparing two nested models. However, in some cases, you might want to be able to compare models that are not nested. These are models that might have different sets of covariates altogether. And the relative fit of models that are either nested or non-nested can be compared using information criterion, such as the AIC or the BIC, which are both based on the log likelihood. And these can be used to select models, but they are not actually hypothesis tests. The most popular one is AIC, which is the AIC is calculated by -2 times the log likelihood of your model of interest minus p, which is the number of parameters, including the intercept. Or you can use the BIC, which is also called the Schwartz criterion. And this is -2 times the log likelihood minus p times log n, where p is again the number of parameters and n is the sample size. And both of the sort of intuition behind either of these criterion, both of them, it's a trade-off between having parameters that make the likelihood larger, which is good, but not having too many parameters. So both of these penalize for having too many parameters in the model, which can overfit your model. So yeah, both AIC and BIC penalize the log likelihood for estimating more parameters. BIC produces more severe penalization. And lower values of the AIC and BIC correspond to more desirable models. So if you have one model that has a much lower AIC than another model, you might want to choose the model with the much lower AIC. However, models that have AIC or BIC close together are considered comparable. So I'll go through a couple examples where we use the likelihood ratio test and the AIC for model selection. And I'm going to come back to that Budworm data that we've used a couple times in order to run these comparisons. So in this data set, we have the outcome is the number of budworms killed. And there are budworms that have different doses of poison and they're different sexes. And in each category of sex and dose, there were 20 budworms in total. And there are 6 different doses that are listed out here that the budworms could have taken. And we're treating dose as a categorical variable, so that means that a dose can have 6 levels. So this chunk of code here just reads in the data and changes dose to a factor variable. Okay, so let's say we're interested in a model with both sex and dose as main effects. And since dose has 6 levels, there will be 5 dummy variables for dose. Then the model of interest will look like this. We have beta 0, the intercept, you have a beta for sex, and then you have 5 covariates for dose, where each of these indicate the dose, a particular dose with the reference group being the dose of 1 milligram. So it'd be dose 2 compared to dose 1. And so this beta would represent the log odds ratio for budworm death comparing dose 2 to dose 1, for example. So we can run this model in R and using this code, and I'm calling this the full model. And you can get a series of estimates, and because we have a different beta we have 5 different betas for the dose categories. We're going to get 5 different estimates and p-values, and these are calculated using the Wold statistic, and they only tell you the significance of one particular dummy variable for dose. However, we might want to actually test all levels of dose at once, since this really is one variable. And how can we do that? Well, we can compare that full model to a reduced model without dose as a covariate. So this is a model that's nested within that full model. And that model would be, I'm just going to write it out on the top here. A model with sex but not dose. And so we're comparing this model, this is the reduced model, to the full model in the previous slide, which is equivalent to testing the null hypothesis that all of the betas that are in front of a dummy variable for dose is equal to 0. So we can code up the reduced model in R here, and we calculate the degrees of freedom, which for our likelihood ratio test, which is the number of parameters in the full model minus the number of parameters in the reduced model, which in this case is 5, because there are 5 of the 5 dummy variables for dose are in the full model but not the reduced model. And then our test statistic is going to be the log likelihood of the reduced model minus the log likelihood of the full model times -2. So we calculated the degrees of freedom in the test statistic here. We know that the likelihood ratio test statistic in this case follows a chi-squared distribution with degrees of freedom equal to what we calculated right here, which is equal to 5. And we can actually use the quantiles of the chi-squared distribution to get a critical value for a chi-square test where you have alpha is equal to 0.05 and degrees of freedom equals 5. And that's what this is calculating here. So again, so we're testing this null hypothesis that all of the betas associated with dose are equal to 0. And this is against the alternative hypothesis of not H naught. So just saying that H naught is not true, or equivalently, you could say that at least one of these betas is not equal to 0. We're choosing an alpha level of 0.05, and that test statistic that we calculated as the ratio of likelihoods is about 113. And the critical value, which also was calculated in the previous slide, is about 11. So the test statistic is much larger than the critical value, so in this case we would reject the null hypothesis. And then you would conclude that at the 5% level of significance, the data provides sufficient evidence to conclude that dose is associated with budworm death. So in other words, you would go with the full model in favor of the reduced model in this case. And I showed you how to do this by actually getting the likelihood ratio statistic yourself and finding the critical value yourself. But you can do this more simply in R using the ANOVA function, which you've probably seen before. And you can use the ANOVA function. You plug your reduced model in first and then your full model. And you want to make sure to specify what test you're using. In this case, we're using the likelihood ratio test. If you don't specify that, you're not going to get a p-value. And it will give you a table that gives you your degrees of freedom, which is the same as what we calculated, 5, your test statistic, which is also the same as what we calculated, and a p-value associated with this test. And here I just tested whether dose was equal to 0, but you could test any set of nested models using this test. So instead I could have a reduced model that is, say, a intercept only model. And a full model that has the intercept and sex and dose in the model. And you can compare these two models in the same way. So next we're going to talk about AIC. So typically AIC and BIC are used in the same way, but AIC, they're just calculated differently. And AIC is more popular for model selection than BIC. So I'm going to use an example of that. So first let's look at the AIC values for the two models that we looked at previously, the full and reduced model that we used for LRT. So to remind you, the full model has sex plus dose, and the reduced model has sex alone. And then we're going to also run this other model that only has dose. So these two models are nested within each other. The dose model is nested within the full model, but the dose model and the reduced model are not nested models. So in this case, you can get the AIC really easily from GLMs that you run. It's actually just returned as part of the model structure, so you can just use the $ AIC to get that value. And for the full model, the 1 plus and sex plus dose, we have an AIC of 49.1, whereas for the reduced model that only has sex as a covariate, we have an AIC of 142.9. And so the better model, generally speaking, is the one with the lower AIC. So we would say that using AIC as a selection criteria for, as the selection for the model selection criteria, we would choose the full model in favor of the reduced model because it has a lower AIC. And this is consistent with what we found using the LRT, the likelihood ratio test. So we can't use the likelihood ratio test to compare non-nested models, but we can use AIC or BIC. So in the previous slide, I ran that dose model, which has only dose in it. And we want to compare to a model that has only sex. These are non-nested models. And we can access their AIC the same way. It's returned as part of the GLM function. And the AIC for the dose-only model is 57.3, while the AIC for the sex-only model is 152.9. So in this case, using the AIC as the model selection criteria, we would choose the dose-only model in favor of the sex-only model because it has a lower AIC.